Yeah, I will wait for 2-3 more minutes, then we will start. Yeah, are you able to hear me? Am I audible?
Yes.
Yeah, okay. Mm. Yeah, for me it is last. I'm not taking the extra class. I don't know others are taking or not, but I'm not taking the extra class. Yeah, so let's begin. I don't think it will take 2 hours today, but let's start. Okay, hello everyone. My name is Rajan Mukherjee, and I'll be taking this live session for NPTEL course on reinforcement learning. I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So, as usual, we'll be solving some tutorial type questions for this week, and I will also give a full review of what was taught this week. So, the session is being recorded, and you can ask any question anytime you want. Okay, so let's begin. So, week 12. Okay, so far we have built an intuition towards MDP problems, right? So we went through the two types of ways we found to solve the MDPs. One was your tabular method, another was your value function approximation. Right. This two we mostly discussed for solving MDPs, any kind of MDPs. Uh, Now, what are the things that was part of MDP?
Tabular matter, you mean lookup table method, right?
Yeah, tabular methods is mostly your DP and your Monte Carlo and TD, right? And value functions, what were those value functions we discussed? Even hierarchical learning is also kind of an approximation, so you can consider it part of that. So these are the two types of things which we noticed in our traditional MDP solving problems. Now, what are the things that were associated with your MDP? The things associated with your MDP was your state function, states, states, action, rewards, and your transition probability, and your rewards, right? These are the four tuple you have for your classical MDP problem, where you have a set of states and a state of actions, and your state condition probability distribution following it, and also you have the reward, right? And what was our goal? Goal was to find out the optimal policy pi. That was kind of our goal in our standard MDP solutions. Now, what are the basic assumptions that we behind the MDP? So behind the MDP, our main one of our main motivation was that we are assuming that given we are at a state sk, so suppose our x starting state was s0, and currently we are at sk. So we don't have to remember what are the states and the actions we have previously noticed. So our observation was only based on the state we are currently at, because that 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 state currently has contains the history itself, right? That presence of our um, presence of our policy at currently that state is basically tells us that okay, the previously it might have gone through these such kind of steps, right? So it doesn't have to, you don't have to remember the entire history of the propagation. So that is your typical MTP solutions, and most MTP solutions we find out using this, like value and uh, like value and your action value pair and your state value pair, right? So those things which we considered. Okay, now why we are doing uh, like so today's topic was POMDPs, partially observable MDPs. Now, one major assumptions uh, which we which we assumed in an MDP was that suppose we are given at a state S, given we are at state S. Our main talking point was that we are able to look at, observe what are the other states there are, right? What are the other states we have? So that was one of the main thing that you will notice, that we don't have to understand that in which state previously is. Only at being at a particular state, we are able to tell that the states, the other all the other states, the observe all the other states and the conditions they are in. So we don't have to look at others. All decisions we can take at ourselves, because we assume that we know the entire context of the MTP, the whole MTP, all the states and all. Now, in a general situation, that is not possible. Okay, so in a more generalized concept, that is a very hard assumption we are making, that given at a state S, we can observe everything, like all the states. You can think about it like you have 10 to the power 5 or 10 to the power 25 states. Does it make sense that we know every at which condition or state the other states are at? That is quite difficult to store for each of them. So a more immediate solution that people think about is your something called uh, POMDPs, partially observable MDPs. So let's look at the example which was shown in the class. So suppose we have a grid world. Suppose we have a grid world like this, and let's say these are empty spaces, and these are the path through which you can let's say we have a robot. Suppose we have a robot, and these are the steps grid switch and go. So at a step, let's say it goes from one of the smaller grids to the another grid, right? Let's say such a concept we have. Now for the robot, it cannot observe everything. Like I'm saying that let's each of these grid, let each of these grid represent a state. So you have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So you have total 26 states, right? Now, uh, the robot basically roams around in this grid world, and it goes from one state to another, right? Now, uh, now for the robot, think practically. Does he need to know what is there here? Like what like does it needs to know that what is the condition here? I'm just giving you an intuition, trying to build an intuition for it. So it is not required for him to know. So to move, he can move. Let's say the robot can move at this kind of directions: east, west, north, south, left, right, up, down, right? By east, west, north, south. Okay. So it can go only in these directions. So what will be the criteria for it to work? So if it plans to go north, so it will check whether there is an empty grid or not, right? So it will try to check if there is an empty grid or not. If I want to, or if it has a boundary, right, or obstacle. Let's term it obstacle. So for movement in any direction, the robot needs to know whether there is any immediate obstacle, right? This is what it needs to know. So since it can move only in four directions, we will maintain a vector like this. Let's say we have a vector like this. So if like suppose we want to find the vector for this state, let's say state 1. What will be the vector for this state 1? Like at position at this state 1, what will be the vectors? Observable features for the robot in this case. It will be, let's say, 0 for no obstruction and 1 for obstruction, right? So here on the north there is no obstruction. So if it was north, south, east, west, so north no obstruction, so it will be 0, south no obstruction 0, east no obstruction 0, west obstruction 1, right? So this is one kind of a feature for the node for your robot at that grid, right? So these are your observable features, or specifically called observables. So you see, it doesn't need to sense all the states on all it needs to depend upon for movement. Only it needs sensing the surroundings, right? It needs to just sense these four objectives, right? So the tasks which we have already, all the algorithms which you have previously seen are can be called completely observable MDP. So these kind of conditions where you have few observable parameters and based on that you take the decision, this is called partially observable MDP. Okay. If you have any doubt regarding this, you can ask. So this is the main crux of what is a partially observable MDP.
What do you mean by like we cannot like we can see all the states in MTP like completely observable. Like if we apply Markov decision, so we can only see like let's say one way Markov process. So just the past state,
So
right?
when you are applying the let's say Monte Carlo algorithm, what do you do? So you pick up select all the possible choices of action and you check and you do a loop over it, right? So for all the states and all. So here you don't have to do that, right? Here you have a specific set of observables, and based on it you make the decision. You don't have to completely go over all of it.
Okay, got it. And
Right.
also one more doubt, like in Monte Carlo, we like sir has written the formula like RT
Mm-hmm.
plus one, right?
Mm-hmm.
So what is like that R? Like that is like actual reward we are getting, or like that is
RT. So
like
whenever it is RT is the terminal reward. So you have reached the last state. So that is the reward for reaching the last state, right? So whenever you are making the any Monte Carlo, what you will do? You will produce like a set of states like S0, S1, S2, S5, S6, and then S7, right? So let's S7 is the terminating state, right? There it terminates. So you have reached your goal. So for reaching the goal, you get a reward. That is what we are mentioning as the RT.
so like
So
that
that is
is
the
like
immediate reward for the S7.
so we can say like that is the actual reward or something like expected reward
No,
only.
no, that
Like
is actual reward. RT in that case is actual reward.
okay, and Q is basically the expected reward, and Q star is true expected reward, right?
Q is your expected reward, true, and Q star is the basically value function. Those are called value functions, right? Value functions are basically estimation of reward.
No, actually, the sir has used like in different lectures like Q and sometimes use Q star.
Yeah,
So
Q star is the
is that
optimal one, right?
okay? And both are like expected, right? Like in expected sense.
Yeah,
Or
both are
like
expected. Both are expectations. So you understand what is an expectation is, right? So
yes, yes.
that is the
Uh,
like any random variable has some kind of expectation. Any random probability variable or those kind of things. So from there, that kind of stuff is for the reward there.
okay. Also, one more thing regarding rotation. There is a V pi and Q pi, right? So one is having this state and the second is having the state and action, both.
Yes, yes.
So in a nutshell, like what is the difference between like in the second we are just fixing the state and in the first we are not fixing the state.
True. So you think about it. Why do you need an action?
Yeah, like why we need to fix it.
Yeah, why do we need action? Right? You need the action to propagate, navigate, right? From one state to another.
Like in V5 also there is action, right? When we move from one state to another. So
But VPI is for all the possible actions, right? When you are calculating the V function, it is for all the possible actions possible, right? So 1 minute. So suppose you are at state
yeah,
SK, right? Say, right. Now there are a possible set of actions that are possible, right here. Say these are A1, AI, AJ, AM, AN, right? And there are several other states it reaches when it takes this action, right? So what it needs to do is it needs to sum up all of it. So that is your value function. So it basically you will see the formula. The formula is quite clear. So you will sum up all of this. Whereas in Q function for a policy pi, what you will do is you know what is the best action here, and you will select that action only and add it up. So in summary, when you are accumulating all the values from the for the state, it's in for V.
but yeah, but my doubt is like, see in V5 as we don't have any action in the formula,
Mm-hmm.
but in Q5 we have an action in the formula, right? Given
Yes.
at state in action. So
Yes.
like, so action is like, in what sense we are like representing action in V5 formula? So that is like I want to
Action.
know.
How are you representing
Like
action?
V pi S is basically expectation of pi GT by
Yes.
S equal to S, right?
Yeah.
So basically, we are having action in this also, right? Like sir has
Yeah.
represented like
Yeah. So let's say let's think about max q. Okay. Max q is a kind of algorithm right. So what will happen in a max q? Suppose your state is and this gives you the maximum return. So maximum value from maximum QA value. So these all. So suppose you are SK. Let me again read out it. Suppose you have this SK, right? So you have A1, A2, A3, A4, right?
yeah,
These suppose so SK comma A1 is basically a Q function, right?
okay,
This state action function value will give you a estimated reward. Like if you follow this path, you will get an estimated reward. So this is also an estimated reward.
okay. So like initially we fix first one action and then
Yeah.
followed like
If you follow one action and take it, that is your Q function. Now what will
yeah,
be the value of what will be the value of SK? Value of SK will be sum of all of this. Weighted sum. Okay, not full sum. Weighted sum based on your weighted sum of Q. Uh, yeah, weighted sum of Q and just nothing else. That is your value function.
okay, okay. So basically, we don't talk about like action in this
No,
V formula. It's
no.
just about like
You,
values,
you,
right?
you have to add up all the action value pair based on the probability.
Okay. And for the action part, like we take optimal action or like we don't worry about action in this V formula. Like it just like the sum of returns, something like that.
For Q, there are specific, obviously, SARSA kind of things is there. You have max Q, right? There are many Q functions, different Q action algorithms.
Okay, okay, got it.
Hmm.
Okay.
So this part is clear, right? So instead of okay, since I have drawn this diagram, let me just say it again. So if here what we will doing, you will just loop over all of these possible action pair or action possibles and take a decision based on it, right? Here we don't have to take it. Here we'll just check all the only on this only on this state value, only on this observable features. I will decide on these observable features.
one more thing in this diagram only. Like in the lecture, sir has said like in one of the states the probability will be higher, and then
Yeah,
if you like go to other state, then it will be lower. So
yeah,
like, what is that part?
yeah. I'm coming to the probability part. Okay, so I was just giving you a little heads up on what is we are meaning by POMDP. So I will come into it. Right.
Okay.
Okay. Mm, okay. Let me share my screen. I have. I will not use the slides now. Okay. So is the text visible? Yeah.
Yes, it
Yeah.
is.
So this is a tutorial from some Oxford or some I don't remember from which was there, Brown University. Okay. Yeah. So I will just go through some of the text and the parts to give you an idea of what is a QMTP and what we are doing here.
Can you share the link for this as well?
Yeah, I will share it. Uh, yeah. So, as I was saying, a POMDP is just an MDP, but what we have here, we have a state of states, a state of action, a transition, and immediate rewards. Like that is the thing which we have in case of an MDP, right? Now, what POMDP extra have? So, these action effects are also same as that kind of MDP. The only difference is whether or not we have observed the current state of the process. We are in a POMDP, we had a set of observations in the model. So instead of directly observing the current state, the state gives us an observation which provides a hint of what state it is in. Okay. The observation can be probabilistic, or we need also to specify the observation model. The observation model simply tells us the probability of each observation for each state in the model. Okay, let me explain it. Uh, let's come here. So in the reinforcement learning part of uh, this POMDP, so earlier we are taking the decision based on in what state we are, and we are taking it on the state action value pair. Okay, we don't have that. So it kind of says that it doesn't know in which state it currently is in. So so let's say let me, suppose our robot is currently here. Okay, right. So in this POMDP formulation of reinforcement learning, think about like this way. So it is currently standing here, but it doesn't know in which state it is presently in, right? So there are 26 states here, but it doesn't know in which of the 26 states it is currently in. Okay. So for how will it then make the decision? That is the problem here. So what it has currently is these observables. So for each state we have an observable, right? So let's assume there are 26 such observables, and let's say you have a table like this. So it will be 0, 1, 1, 0, 0, 1, 0, 0. So suppose this is a state. For each state, there are different such observables, right? Right. So suppose you are currently at some state, and there is this distribution for each state. So previously it was S A P R. Now you have a gamma, that is your observable like, and you have what is the function they were discussing it. It's a phi, where phi is a probability function over S, right, state S, right. So what will phi give me? What will phi give me? So phi will give me the phi will give me a probability distribution based on it, based on the current state it is in. So suppose we are currently at this state S. We are currently at this state S. Let's say we are currently at state S, and we observe that the what will be the observable here. So in this block, if we are currently in, what will be the observation here? What is the observation we are getting? Think about like this way. So north is a obstruction 1, left is a west is a not an observation, north south east west. So north south both there is an obstruction, and there is no obstruction here. So here it will give me 1110, right. Now it gets this observation, and now it will look at this function phi. What does phi have to tell him? What does it require to formulate an MDP? What does it require to formulate an MDP? It has the actions. It has the list of actions. What it needs to know? What state it is in, right? It needs to know in what state it is in. It only has the observable. It doesn't know in what state it is in. So this phi will give him a probability distribution of what state it could be in. Is this understandable? Or I will repeat again. So suppose the vector is 1 1 1 1 1 1 0. Let's say the vector is
Vector is like represented like top, right, bottom, and
yeah. So north, south, east, west. Okay. Yeah.
okay.
So north and south, you see there are obstacles, and east west there is no obstacle. Okay. So how many such 1 1 zeros are there? 1, 2, 3. Sorry, 1 will not be there.
6, I guess.
1 will be there. This one will be there.
No, no.
Yeah, it will
Not
be there because north and south there is obstacle. Yeah, north and south there is obstacle.
okay. Yeah.
Yeah. So
We are
one,
not
one
considering
two,
right now.
yeah, right. So north and south there is obstacle, and 1 2 3 4 5 6 7 8 9 9 10 11 12. Right. So there are 12 such locations where it could be currently present, like 12 such states. So 1110 is represented in 12 states, right. Now it is not possible that now how are you going to differentiate between in which state it is currently in and which state it's currently not in? Here comes the phi function. So phi will give us a mapping of the probabilities that in which of these 12 state it can possibly currently in. So phi give a mapping in which of the possible 12 states it can be currently in, right? So suppose uh, P1, P2, P3 dot 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 P12 it is having, and there are some probability uh, attached to all of them, right? So based on it, it will if someone has a greater probability, it will pick that one up and do the entire computation. So 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 here what we have, basically we have an MDP plus observables plus what this distribution of observables over state, right? Right. So once it gets to know in which of this in which of this state it is in, what it can do, it can do a normal NDP problem, right? Once it's know the using probability which one, in which state it currently in, then it can definitely tell you with it can definitely give you your how you are solving MDP. That is, it can give you a value function and Q function regarding to it. What will be the next state and do it. So that kind of transition you can make, right? But what is the issue? What remains the issue if it is so straightforward? So if you have this, so once you have seen the observable and make this got the state out of this, suppose you have got a state S, so for you then solving MDP is not an issue, right? But here was the catch. What is the catch? There is one catch. The catch is this is a probability, right? So suppose this one will have 0.7% chance it is in this has, and 0.22, let's say this is 0.03, this kind of, let's say, probabilities are there, right? It is not something that you will select always the best one, right? It is not, then you will not be able to operate it correctly. So you can think about it like this, like, so if you are uh, if there are so many possible states possible, then it will be a very big chunk of function then, right? So many transitions you have to take into consideration, so many states. So yeah, not previously if you are solving one MDP, then only one state is enough for you, but let's see here there is a total distribution, you have to consider all of them to get you a like a value function based on it, right? So that there lies the complexity here. There lies a big complexity that you don't know the which states it could be. It is a probability distribution. It is a continuous function. So so previously in MDP, while in MDP you have discrete states in POMDP, you have a continuous function as state, right? So while previously you have any discrete states for the MDP, here you don't have the discrete state. You have rather a continuous function, a probabilistic function.
You have written like discrete state, right? So like continuous state and discrete state, what do you mean by that?
Discrete means fixed. Let's say fixed states. If you are like complain with have complain with discrete, then let's say fixed state.
Okay.
Now you have a continuous function. So let's come back to this tutorial. Okay. So in our MDP problem, normal MDP problem, we have to find a mapping. What we have to find a policy is basically a mapping from states to action, right? So while in MDPs our problem was to find a mapping from states to action, in POMDP our problem is to find a mapping from probability distribution over states to action. Correct? This is what I have been saying, right? So previously you have a mapping from states to action. Currently we have a mapping from probability distribution over states to action. Basically you have a continuous function. So we'll refer to this probability distribution as a belief state. So this is called a belief state. Probability distribution over action is called a belief state. Uh, so this is your belief state. Okay. So now,
Why we are saying this as a belief, like we don't know like which state we are in. That's why we are saying it.
it is just a nomenclature. Okay. So, so you will understand why it is called this probability distribution is a belief state or not. Like why you are using probability distribution. Let's go through this example. You will understand why it is called a probability distribution and how easy it is to do it. You don't have too much think about it.
Yeah.
Okay. So if you look at this figure, you have two states. So we will be using this two state POMDP as our example. So these are two state POMDP. For a two state POMDP, the belief state, we represent the belief state with a single number. Okay. Since a belief state is a probability distribution, the sum of the probabilities must be sum to 1. So with a two state PMDP, if you are given the probability of being in one of the states P, then we know the probability of non being in the state must be 1 minus P, right? So therefore the probability the entire space of belief states can be represented as a line segment. The figure below shows this. We have made a line segment with a significant width. So what you have is there are two states. You have 0 and 1. Okay. So what will be the belief state in this case? Belief state basically a probability distribution over states, right? So think it as of a variable, let's say P. What does P denotes? Let's say P denotes the probability with which it is currently at state 0. Let's say that is what it denotes. Let's say there is a variable P which denotes with what probability it is currently in state 0. Right. Then what is the probability it is not currently in state 0, or let's say in state 1? 1 minus P. Right. So your belief state will be something like this. So you are currently at state 0 and you are currently at state 1, right? And here is your distribution, let's say. Right. So let's say currently your something is here, so you are currently at here, let's say. So what we are saying is probability that the that the object is in state 0 is p. Let's say with pre-probability we can say that it is currently at object at place 0. Then with 1 minus p probability we can say that we are currently at state 1, right? So as you roll the wheel over this, let's say over this straight line, our probability will increase and decrease. Suppose currently we are here, so let's say, so it has 75% chance that it is currently in state 0, right? Therefore only 25% chance it is that it is not in it is in state 1, right? So as it moves closer here, let's say suppose someplace here, then what it will be, let's say it will become 0.25 comma 0.75, right? This is your belief state or observables, probability over your state, right? Is this understandable? Yeah. So previously, what we are doing, we are trying to solve the MDP based on your state action pair. What we will do here instead is use the belief state action pair. Okay, let's come back to it and okay. Let's say currently we are at belief state, this yellow dot. So you can see this yellow dot. So currently let's say we are in this, we are belief state in this yellow dot. Now, so what you have here? You have two states S1 and S2, two action A1 and A2, and three observations Z1, Z2, Z3. Okay. Now, suppose it takes action 1. Suppose it say, let's say it took action A1 and it goes to Z3, observation Z3. Previously it was in observation here, it goes to observation Z3. Similarly, let's say it observes A2, it goes to Z1. Right. Similarly, the belief state can observe action A2 and go here, and Z3 and go here. So these are the various kind of transition it can make. Being at state, being at this yellow belief state. You see the notice, you notice that all the transitions it makes are also in some belief state. It could be one state here, it could be one state here, it could be this state or this state.
So it's like belief states are different from normal states, or
Yeah. So what did I say about the belief state? So this is your belief state. So what is your normal state? This is your normal state. 0 and 1. This is the normal state. So I don't know which state I am. I am currently. Let's think about this. I don't know in which state currently I am. But I know with probability that I can be in this state or that state. We know the probability with which I know the currently probability with which I could be in this state or that state. So I get the probability here, and using this probability distribution I choose some actions. So okay, I have this probability distribution. I choose some action and take that action. What will it do? It will take me to another belief state or observable, right? So let's say it makes a move by by taking action A1. Let's say it takes action A1 and goes here, and here is the new belief state. So let's say previously it was 0.29, so this, let's say it becomes 0.13, 0.87. This is the new belief state it gets after observing, let's say, A1. After observing A1, it goes from this belief state to that belief state. Okay. Previously, it used to happen what? It used to move from either 0 to 1 or 0 to 2 or something like that. What the difference basically is, previously you are considering the entire problem based on normal states, discrete state, fixed states, but now you are using the belief state to determine such kind of uh, transitions.
So
Now that
like at the end you need to like transition to the actual state, right? Only.
no, this the entire value function in this case will be based on belief state.
So
So
like how we can reach the actual state, because like in real scenarios there will be no given state, right? So
yeah,
like
but belief state that means here it is observable, right? So at the end of the day, you will reach some observable. Here you are moving from one observable to another.
and what is the goal here? Like where we have to reach?
Goal is the terminating state, some kind of terminating state, right?
Like what I'm understanding is like there are two states, 0 and 1, right? And one of these is the goal
Yeah,
here.
yeah. Let me show you. Suppose you are currently here. You are currently here, right?
Okay.
These are some observable, right? Basically, this is an observable, like this kind of some place in here, and you want to go here. Let's say not that one. Yeah, let's say you want to reach here. Wait, this one also has some observable. Now you get it. How I'm trying to say. What I'm trying to say.
And which one is the goal?
Goal is to reach here.
Or and like observable will also lie
Obviously,
there.
observable there. What it will be? It will be some state that will be, let's say, let's say the observable here will be um, some, let's say, here it is two sides. Okay, so this is becoming north is 1, let's say, not probability north is 1 is 0.9, let's say 0. South is, yes, it is 0.01, uh, east is 0.07, and let's say 0.85. So this is a belief state, maybe currently it is close to it, right? So that kind of belief state you want to reach.
Okay. Got it. And one more thing is like we are having SAP in that tuple, right? P. So P is the probability or anything.
Hmm?
So we are having the tuple in POMPT SAP, R, omega, and O, right?
Mm-hmm.
So what is the P here? That is the probability, or
So this is your belief state, those kind of thing, and this one is your observables, list of observables.
yeah, P is the probability, right?
P is your transition probability.
Okay.
Any more doubt? Okay, so let's move on. So, so as I was saying, this is a continuous function, right? So from 0 to 1, uh, since there is only one, so you can represent it as only one variable, right? So as I was saying, you don't need both p and 1 minus p because those are complementary. So based on a function, you are describing the position, right? So when the value of p is near to is less than a certain value, then it is being state 0, and let's say as you go towards 1, it increases, right? So this is your typical like value function over a Belief space. And you see it is a continuous function. It is not a discrete function. Okay. Now here lies the problem. So here lies the problem. So you see these are all discrete points. And these are if you try to sample it, so let's say you are trying to sample it. So there will be infinite number of samples, right? While there are fixed number of states. So how many there will be belief states? While there is fixed number of states, how many belief states? It is basically infinity because it is as you can see, it is a continuous function. It will be a continuous function. So the function will be something like this. So initially, as suppose this is p, so p is with the probability at which it is state 1. So initially it will be high, then gradually it will come down low, right? So it could be a graph like this. So obviously there are multiple local minima and local maxima, multiple such sampling points you can do on this curve, right? So there lies the main problem of POMDP. Like how are you going to compute the value functions, right? So give suggestions how it is possible that you are trying to find the value functions. So you know what how you're trying to follow the value functions, right? Whenever you try to do a value function, find a value function, what you will do? Value iteration and then improvement, right? So those two steps are possible required, right? And what you do in each case, you sample a trajectory and compute the value function based on it, and you update the function, right? Every time you draw a trajectory and you compute the value function and update the value function based on it, right? Same stuff goes here, right? If you're trying to do the same thing on belief state, let's say you're trying to do the same thing over belief state, what will be the issue? The number of jumps you are making or the number of steps you are going is just infinity because it is a probability distribution. It's just infinity. So the one thing you can do is you partition it, or you get a feature finite set of features based on that value function, based on the distribution curve. You say you sample some, you do some sampling and take out some fixed points. What I mean to say is, let's say if this is the curve you have, let me draw a better curve. Let me draw a curve. So let's say this is your value function curve. Right, let's say this is your value function curve. What you will do is you will try to sample it like this. You will try to create some sampling like this. This one, this one, this one, this one, this one, this one, this one. So you have 1, 2, 1, 2, 3, 4, 5, 6, 7. Right. So you have been able to divide you are have been able to sample and divide the continuous function into smaller chunks. So while previously it was an infinite number of steps you are taking to move from one belief state to another, now see you can take 7 states and do the jumping. You just need 7 states.
But
Yeah.
what is the parameter like that will decide like how many discretization we need to do, or like how many?
That is depends upon specific algorithms, and you set the parameters that I do want to do this divide this graph into 7 samples or 10 samples. You can do that kind of sampling.
Like depends on the problem.
Yeah. Now whenever you are making a jump, you are making a jump from one discrete uh, belief state to another discrete belief state, and there is nothing continuous anymore if you are doing something like this.
So like it's like we have formulated this problem as MTP.
Yeah, now it is an MDP.
Okay.
Now it is a perfect MDP. MDP for belief states. Now you don't have to think about all those transition on based on probability and all. Obviously, each of them these belief states have some kind of probability, but these are still continuous, not continuous. These are kind of fixed points. So as you can see here, they have done the discrete sampling, and then it divides the entire belief space into 3 parts: one, two, three, 8. Okay, so now I will give you a idea of what how you are determining the value function, how you will determine the value functions. So take a look at this diagram. Mm, so suppose you have something like this: 0, 1. You have been able to divide the states right. You have something like this. So how will you calculate the value functions? Suppose you are in currently state S1. Suppose this is S1 and S suppose this is S1 and S2. Okay, and currently suppose you are someplace like here. Let's say it is 0.75, 0.25. Okay, the belief state. Let's say now you can choose two actions. If you are currently, let's say, if you are at S1, then A1 equals to 1, A2 equals to 0, let's say. And if you are at S2, A1 equals to 0 and A2 equals to let's say 1.5. Okay, so how will you compute the value function? Suppose this is your belief state. So if you choose action 1, belief state, so V for A1, what it will be? It will be 0.5 into 1 plus 0 into 0.25, right? This is how you compute the value functions. And V for A2 will be 0 into 0.75 plus 0.25 into 1.5, right? So which one you will choose? So here the total value will come out to 0.75. Here it will come out to, what will be, 1.5 into 0.25. What will be 1.5 into 0.25 is 0.375. 0.375. Okay, so value function of A2 is 0.375, and for A1 it is 0.75. So basically what I mean to say is Q of, so let's say the belief state is x, Q of x given A1 is 0.75, Q of x given A2 will give you 0.375. Clear? This computation is quite similar to how you are doing your like after you calculated this, it's quite similar to how you are doing your previous MDB solutions, right? So if you have to find the one-step reward, this is how you are going to do it. You know the actions, what is the reward corresponding to the action, and you multiply it with the probability of your belief state, that is probability that is currently in your belief state, and you get the value p, action value p's. Right. So this calculation is okay. If you understood this calculation, you can save me, or I will repeat.
Yeah, yeah, got it.
Okay. So typically speaking, this is your one step ahead, uh, one step ahead reward calculation, right? So you know the reward for action A1 at H1, and this is the reward you get. So reward RA1, RA2, RA. So this you know. Now basically you can write it as R of A2 is 2 and this. Okay. Right. So if you are at this belief state, and if you take this action, you get the value of this belief state, right? So that is one arm away immediate reward you are getting. So this is the immediate reward. So to compute the q value, or so if you have to, if you let's say if you are trying to fetch the q value, so you only not only need the immediate reward, not only the reward, but the sum of consequent value function. Do you have to make any change in that part? So once, so remember the transition is from one belief state to another belief state, or from one observable to another observable, right? So there will be no much difficulty after that. Once you have conquered this part of the algorithm, this initial part of the reward simulation, that simulation kind of thing will be remain same. So the jumps you are hop jump you are doing, it will follow the same algorithm, except instead of normal state, you will be using observables or belief state.
So basically, in this algorithm, we like follow the same thing. Like we take the path which gives us the maximum reward,
Yeah,
and here we are having immediate rewards.
yeah. Just how we calculated immediate reward, you will follow the same procedure up till to the end, or whatever is your terminating state you are trying to reach goal state. Okay. So this is what somehow I wanted to give the introduction for PMDPs. So there are much more topic inside this. So if you want to read the whole, you can. I give you the link. You can check that link and read it. I didn't find any better source than that. Okay. So let's get to the problems for this week. One by one, let's try to solve it. So this is the question number one. In a partial observability example that we saw, there are some observations which uniquely identify the state of the environment. Right? There are some observations like left, right, like east, west, north, south, and those kind of things. Suppose in a problem, no such observation exists. I.e., there is no observation which allow us to exactly determine the state of the environment. So there is no observation which allow us to exactly determine the state of the environment. In such problem, is it possible to be sure which state you are in given only the sequence of observation? So, so what it is saying is there are, suppose in a problem no such observation exists. There are some observation there is no observation that allow us to exactly determine the state of the environment. Why no?
observable or probabilities that corresponds to observable. So we are kind of lost, like we don't know how to navigate through this, right? Because the probability of observation is not there.
Kind of true, but any other thing? See, what we have here is you have observation, but these observations will not allow us to uniquely identify the state of the environment. What it is saying that we don't have the phi. We have the observables, but we don't know the phi, the mapping. The thing is we can identify. How we can identify? Think about an example. In a small example like this, let's come back to this. Suppose you are currently here and you have got an observation, but you cannot determine that where currently you are, which state currently you are in. You have got an observation. You also have with you the previous observation. Let's say you have stored your previous observations. Let's say you have got, so what is this one? This one is, so only east is 0, so 0 0 1 0, right? Suppose the previous one you observed was this, let's say it was 1 1 0 0, right? So this will give you an idea that you are currently here. How? Because if the previous state was this, what it will be? If the previous state was this, what it will be? It will be north south. Oh, sorry, I made a mistake. This one will be, this one will be 1110, right? 1100, and this one will be 0011, 011, right? So you see, by observing the previous state, previous observation we have. So if you have observed previously 0011, so you get an idea that in which state you can be now, right? That's why short history will help you in observing in such a case. Now I got it, like why we will be able to get an idea in which state we are currently. Because if you maintain a history, in that case you can make it up. Notice maintaining history is not a problem because this is not a full MDP. These are partial observable MDPs. Like it doesn't fulfill the criteria of an MDP. So you can maintaining such a history is not a problem. Even maintaining such history, but even
Yes,
maintain,
so
yeah, even maintaining such history will be much more helpful, because that will help you in improving that probability distribution function, right? Like if you maintain a history, like uh, there is a high probability you are making a transition from here to here, so you know with high probability in which state you can be, like the probability in that case will be high. That those kind of jumps knowing is much more important. Yeah, what you're saying, Saran.
yes, sir. So I think given the probability is like one observable 1100,
Mm-hmm,
could
mm-hmm.
be one of the like as we discussed, it could be one of the 12 states, right? And then we compare that 12 states with the the
Yeah,
0010.
yeah,
The,
so yeah,
so every you need to 12 comparison need to be done, no? Like this algorithm.
not necessarily. You only need to get what is the current observable you are getting and what is the previous observable you have. That only helps you currently to get it right.
Oh, okay, okay, no problem. Got it.
Hmm. Okay. So the correct answer is yes, by maintaining a history of previous observables. Okay, so let's go to the next one. Suppose some of the actions that are available to an agent in a partially observable state have non-deterministic outcomes. Yeah, anyone? What?
In the previous question only,
Mm-hmm.
it is like history-based method which sir has talked about in the lecture.
Yeah, kind of. Yes. So, like, once you are deviating from an MDB, you can introduce such stuff, right? Uh, so when you are doing a research work, like, I understand this somebody has discovered it correctly, right? So once you are deviating from MDB, you can use such kind of stuff like some amount of
Okay,
history and all.
yeah, got it.
Yeah. Suppose some of the actions that are available to an agent in a particularly observable uh, environment has a deterministic have a deterministic have non-deterministic outcomes. How would this impact the agent's ability to determine the state it is in? Suppose there are some of the actions that are available to an agent in a particularly observable environment has non-deterministic outcomes. How would this impact the agent's ability to determine the state it is in? It would make the determining the state easier. It would make determining the state harder. It would have no impact in determining the state.
I guess B, state harder.
Why?
then there will be more stochasticity and like
Yeah, yeah, correct.
randomness.
Correct, correct. So, so already you have enough non-deterministic elements in it. So now you are adding, you are saying that the actions are also a non-deterministic outcome. That means the action you are selecting, it doesn't take you only to one possible observable environment. It is going to take you to different observable environment. So that is quite making the job more nastier to find out the like next state easier, not easier. It is making it much more harder. Okay. So if I have to write something, I will write it like this. It is harder. It is the agent not be sure that agent not be sure what the effect of taking an action in a state so agent will not be sure the effect of the taken action in a state is because you are saying that it has non-deterministic outcomes, so it will just make his job much harder. Okay, so let's go to the next one.
One
Yeah,
question, sir.
yeah, yeah, yeah.
So is the the wording partially observable environment? Uh, is it? I mean, like, is it like what happens if it is a fully observable environment? Does it make any difference, or it has no significance?
Yeah,
Whether it's
so what is a fully observable?
even if it is fully observable, then the actions are,
What is a fully observable? It is an MDP,
yeah,
and partially observable is a UMDP. So
correct.
what you are saying is that first of all, pure MDP will not allow this kind of nonsense because MDP is deterministic, right? Your action state action pairs have to be deterministic, else it will not satisfy the condition of your MDP problem, right? When you are formulating an MDP problem, suppose you have founded a policy pi, it has to take a deterministic action, right? It cannot be something based on some random variable choosing something out, right?
Okay,
Is
okay,
that was your question, right?
yeah,
So like to confirm whatever we have studied before, UMDP is deterministic, like the actions we are taking.
Yeah, yeah. So for MDP you have that transition distribution, right? That gives you a with a probability that which action is much more to be taken and all. So that basically gives you a deterministic action choice when you are when you have defined a policy. When you have defined a policy for training purpose, okay, you have a transition and you need it. But for once you have defined an training, you have done your training, you have found out the best possible policy you have, then it's fully deterministic. There is no issue. What it is saying here, suppose after even training it has something called non-deterministic outcome so for each state, that is not possible.
Got it.
Okay, so let's come to this one. Referring to partial observability example considered in the lecture and assuming that there is no noise in the sensor outputs. Is it true that all observation sequence of length 3 or more results in elimination of uncertainty regarding the position of the agent in the environment? So it is saying, referring to a partial observability example considered in the lectures, and assuming that there is no noise in the sensor outputs, is it true that all the observation sequence of length 3 or more result in elimination of uncertainty regarding the position of the agent in environment? It's saying that suppose you have stored more than 3 observation. Can you determine the state? So it's in simple terms, it is asking, suppose you have saved 3 observations, right? Last 3 observation you have saved. Can you determine the state based on it? So let's come back to this example. Can I copy a frame? Fool. Okay, so suppose so what's your view here? Can just observing the last 3 states will give you a will allow you to determine the state at which you are in? Some views. Okay, so let's see this example. Suppose these 3. Let's consider these 3. List 4. Okay. So your agent has moved from here to here. Let's say. So what are the observations you have got each time? Each time you have got. Let's say this. Yeah, this example has a little bit problem. Okay, let me redraw it. and we'll be using the same notation. North, south, east, west, let's say. Okay, so consider this part. Suppose your agent or the robot is moving from this state to this state, right? So what are the observations it is gaining in this point? So this it is gaining, what it will be? What will be the observation here? North, south, 1100, 1100, 1100. Did I draw again the same thing? I'm not redrawing it. Yeah, 1100 and 1100. Right. So it has got four history sheets, right? Now if you observe, this will also be same. 1100, 1100, 1100, 1100. Again same 1100, 1100, 1100, 1100. Right. So you see, by determining the last four observable state, you are not able to determine in which state it is currently in. Right. It could be any of these three. It could be this one, it could be this one, or it could be this one. Right. Or if you move from this to this also, you will not be able to understand. Right. Let's say you use a specific direction also along with the observable. Let's say give a direction, then only you will be able to understand. Even then only also you will not be able to understand this. Right? So the answer will be no, because you see that by example, for example, that even if you maintain some more than three history, it is not always guaranteed to give you the correct state you are currently. You sometimes it can give you, right? Just as we saw the example, like here, like when you are moving from, you are currently here and you you get the previous observation like here and here. That time you can differentiate, but it is not guaranteed that all the time it will give you a correct. You can determine the correct state by observing the history. This one is clear. Any doubt? Okay, so let's go to the next one. So to solve a POMDP, partial observable MDP problem, suppose you decide to maintain belief states. Okay, now you are maintaining belief states. Would the estimation of belief states benefit from access to the history of the observation and not actions? Access to the past observation but not action will improve the belief state. Access to the past action and not observation will improve the belief state estimation. Access to the past observation and action will improve the belief state estimation. Access to the past action or observation or actions will not improve the belief state estimation. Right, what it will be? What it will be? I see. So, so far what we have observed about history. So what you have observed about history or observation? Quite
I
dialogue.
think it will not make the effect. Like Sir said, I think in the history we don't like maintain beliefs.
Yeah, I will come to it. Okay, I will. So, what we have seen about history? Why you are using the history? So, by using history, we were trying to improve to improve the determination of the state. Okay, so this where was our target to use the history to improve the determination of the state, in which state it is present in. What we observed that it helps sometime, but it doesn't help all the time. Sometimes it helps. Result is result. Sometimes helps, but sometimes don't. Right. So this was our motivation between above uh, observations, history of observations. Now, estimations of belief states. So that was instead of estimation of value function of states, we are trying to use belief states. Now, when we are using belief state, we saw that value function estimation in belief state is basically what? Basically, it is a continuous MDP, right? So we saw that for belief state transitions we are making, or the value function estimations we are making, trying to make, or the Q value functions, what we are using, we are using basically the same MDP concept of value iteration and all. Only difference that the MDP here is continuous, and we saw that partition of the continuous function into some samples helped us determine, help us in shortening the complex process of finding the value function here, because it will be infinity in that case, right? So does now now does history helps in an MTP formulation, MTP value iteration formulation and all? The answer is it has no found there. It doesn't use the history. It determines the next state based on the current state, right? So when you have a continuous MDP, when you are running the MDP on a belief system, so it doesn't help. Maintaining history doesn't help in that case. So correct answer will be access to past observation or actions will not improve the belief state estimation. Because once you are doing the estimation in belief state, you are assuming that now you will follow the Markovian process, right? And you will use those value functions to determine the Bellman equations and value functions to determine the policy. Only difference we saw was that we are trying to use a uh, proper sampling process to determine those curves, right? So correct answer will be D. Okay, so let's go to the next one. Suppose you are given a problem in which the agent is able to determine the state it transitions to after each action taken by the agent. However, the state space is described in a manner in which requires the agent to consider information in the current as well as the latest past state in the sequence to make decisions. Is the problem so defined an MDP or or POMDP or neither? Can this problem be solved using Adel technique we have studied? So what you have? You have a problem in which the agent is able to determine the state transitions to after each action has been taken by the agent. Okay. However, the state space is described in a manner in which requires the agent to consider information in the current as well as the latest past sequence to make the decision. So, if it is a state S, SI, it can make the transition with proper deterministic way to SJ. But for that, it requires history. It requires I minus 1 information. So it is an MDP or pure MDP or neither. So it is
Neither.
huh?
Neither.
Yeah, it is a neither. It is not MDP because we are maintaining one is I minus 1's history. So it is neither. So it is neither. Now, uh,
Can it be like two-state Markov? Like what we actually say that like if the Markov process depends on previous two states, can we formulate this problem like that?
again you can say
Yeah, like I'm saying, like Markov, we are assuming that Markov state is depending on the previous latest state, right? So can we formulate this problem as like the current state is depending on the previous two states, like that? So this will be
yeah, but
MDP.
that is not an MDP, right? That is not the one of the other techniques.
Yeah, but like kind of like because we are in normal MDP, we are considering only the past one state, right? So that is like two state Markov or something.
Yeah, so what you can do is, yeah, you are kind of correct, right? I will say. So what you can do is, you can make a subset. Like you can, so if you have a set of S, what you can do is, you can make a subset of, like say, MC2, right? You can do something like this. MC2 means from this subset you consider pair of sets, two pair of sets, right? So let's say you select SI, SJ, and make it a new state. Let's say okay, what can I say? Let's say I denote it by uh, delta I, something like this, delta k, right? Something like this. So what I am saying is, you divide uh, the problem such that you take two states, you merge it, and you make it a new state. Then you don't have to it is now not a, so the history like si minus 1 si, right? So it will be a single problem in that case, right? Like single state. uh, so if let me be more clearer. So suppose, so the here is your set, you are creating a subset or superset, you can say. You choose, you choose two such pairs, okay? You choose, let's say, si sj, okay? So so si sj will be added. So let's say delta is the delta new set of states. So si sj will be added to delta, will be added to delta if I is equals to j minus 1, right? So if like in a trajectory you are expected that is j minus 1 will be the previous state of sj, then you can say that okay, you don't need the history now, you have marked these two states sj and sj minus 1, and that state pair you add it into this new delta delta set of states. So this one you understood. So now it will become an mdp. Now you don't have to maintain two. So what Harshit was saying is correct, that basically it is a two-step mdp, but what you are doing is you are merging both the states to consider it as one.
Actually, I'm a little bit confused also. Right?
Okay.
Not convinced like that.
Yeah. So what does the agent need? Agent needs the one step back history also, right? One step back state
Yeah.
also. It needs to know that,
Yes.
right?
Yes.
Yeah.
Yes. Correct.
Right. So currently let's say it is in si, right? And previous state was si minus 1. So what I am saying is merge those two states and form a new state. Now the agent will don't need to know like what was the previous state. Now it will have the history of both si minus 1 and si.
So, like in general, like we have to assume like it will be one state MTP, right?
Yeah.
Like in
Yeah.
most of
So
examples.
we are creating a new set of states. So so our goal is to formulate it as an MDP. So what you need as an MDP? You need a set of states such that it doesn't like it don't have to maintain the history. So here we need history. So what you will do? We will merge both the states.
So, like in general, we are talking about, because like it can be like this question can be formulated as like two state MTP or
Yeah, but
like
two
as
state MDP is not your formulation for reinforcement learning problem. Right? For reinforcement learning
yeah.
problem, you need that the current state you are currently in, that will hold the history. It doesn't have to depend on previous states.
Okay, yeah, got it.
Hmm. So correct answer will be D. Okay, so let's go to the next one. So recall the example of a partially observable environment in the lecture. Suppose the goal in this problem is to reach the bottom right corner with usual -1 reward for each transition. Assume the agent starts to cell below the top left state. The first action selected by QMDP procedure is to move down, assuming the deterministic action count outcomes with no noise of observation, as well as the use of QMDP procedure when the underlying MDP procedure has been correctly solved. What can you say the optimality of the agent's policy in such a scenario? Option A, the agent will follow an optimal policy to reach the goal. Option B, the agent's policy to reach the goal will not be optimal. Option C, the optimality of the agent's policy towards reaching the goal in this scenario cannot be determined with certainty. So it's a fundamental question. Like this is a very typically easy question. There is nothing. So it's saying that we are starting here. We are starting here, and your goal is to reach here. So you are using QMDP. So QMDP is nothing. It's the same of PUMDP, but Q function version of it. And what they wants to know is like will it be able to find an optimal solution? So what can you say about the optimality of the agent's policy in such a scenario? So it will be able to reach an optimal policy because after you have determined like because you will be using the belief state, right? So belief state will ultimately give you an optimal policy, like because underlying it you will be using the MTP. So optimality will not be issue. It will, you will be able to reach the an optimal policy with to reach the goal. You will be able to get an optimal policy to reach the ultimately. Okay.
In this question, okay, let's say uh, it was a stochastic action. So will the question, will the answer will change?
What do you mean by stochastic?
Like assuming stochastic action outcomes. Like,
Like
okay, in MDP we cannot have a stochastic action.
yeah, because the underlying belief state is you will be following an MDP.
Okay, oh yeah.
Okay, so that was the end. Thank you for joining. Okay, this was the last session. Okay, so if you have any doubt, you can mail me. Or
Sir, so since today is the last session, can you give your, I mean, can we contact you for any further, sir,
yeah,
references?
yeah, you can contact me.
What is the email or?
So I can give you my website. Like there you'll get the email.
Oh, okay, okay. In the website itself. Okay.
Yeah. So you can
Okay.
find it in the website. So it is there.
Okay. Perfect.
Okay, so thank you for joining, and hopefully some other course of NPTEL you will choose again next time.
So like, do you have previous questions also for
Uh huh.
practice?
Yeah.
Some previous questions,
No,
main
no.
question.
I haven't taken this one before. This one's the first time I've taken.
Okay. Like, do you know like how to access that or
So the questions that has been asked you in the in your daily assignments, those kind of questions will be there.
yeah, but like to practice more questions.
Practice more questions. I mean, where will think it?
Okay.
Yeah. Look. So you understand this is very practical subject. Like okay, you have been thrown into a theoretical model, but at the end of the day, it is a very practical subject, and people are writing codes constantly based on it. So I hope you understand the concepts. That's more important.
Yeah, yeah.
Sir, what will be the pattern for the paper?
It will be MCQ. It will be MCQ. I have seen that NPTEL questions are generally MCQs. Okay. So
So solving the assignments will be sufficient for to pass in the exams, or we have to basically go through with all the videos of the professor.
uh, I will say give the book a read. Reading the book is 100 pages, something like 100 to 100 pages. But also you just need to remember the concepts, nothing more, right? 100 pages. Mostly the book is not much has been covered from that. It is mostly 100 pages and more. So any more doubt you have?
No, sir. Thanks a lot for your time. Actually,
Yeah,
it was very, yeah, the entire series was very useful information. People like me without any knowledge about the
reinforcement learning.
reinforcement
Yeah,
learning
it's fine. Like
have required, yeah. So much
so, I will say
information.
that go through the book again. Like the book is best.
Yeah,
The student
thank,
book is very good.
yeah. Thanks a lot.
Yeah. Okay. Thank you for joining.
Also, sir, like we have understood like view MTP and other things. How to implement this like practically? Like, do you have any resource?
Yeah. So OpenAI has something called Gym Library. You can search something like that. Previous first few lectures I was giving some code reviews also, like of some of the like Monte Carlo and something like that. But they have this great like gym library. By most of it is called gym OpenAI.
Like, do you have that notebooks available? Like,
Yeah,
can you share
that notebook was there.
in your
Okay.
GitHub profile?
No, no, it is there in non-graded assignments solution. Where I will get. Yeah, so non-graded assignment solution. I don't know, and doesn't they give it after when you are solving it? Doesn't they give it that time? Like just you need to click it on and they will give you right the marks whether it is correct or not. Oh, detailed solution. I don't have. Like for practical, I haven't gone through these lectures, but Hugging Face also has a RL tutorial. You can also check this one. This is also this I haven't checked, but I have seen there's NLP course was good. I guess this one also will be good.
This is another course for reinforcement.
Yeah, this is a very like this Hugging Face. Other courses are good. I guess this will also be good. So you can check it out.
I will.
Okay, so I will end the call now. Okay, Tata.
Yeah.
Thank you for
Also,
joining.
sir, one more thing. Can you share the notebooks like you have?
So it is there in the like the Google Drive, right? The Google
Okay.
that
Okay.
is
Okay.
there. Okay, okay. So I'm kind of disconnecting the call.